Welcome back to the deep dive. Usually when we sit down here, we're unpacking a messy human story.
Right.
You know, a corporate collapse, a historical biography, maybe a political scandal. Things where the rules are, well, they're flexible.
The gray areas?
Exactly, where
Yeah.
people can talk their way out of trouble.
Mm-hmm.
But today, we are doing something completely different. We are looking at the only rule book in the universe that has absolutely zero gray areas.
Zero.
I'm not talking about the law or your employee handbook. I'm talking about the operating system of reality.
We're talking about physics.
And before you reach for the skip button because you're having flashbacks to high school calculus or, vectors drawn on a chalkboard, hold on.
Yeah, please hold on.
Because the source material we have today, it's titled The Operating System of Reality, A Survival Guide to Physics, isn't about getting an A on a test.
No, not at all. This research stack is fascinating because it strips away all the theoretical niceties. It's not about finding $6. It's about why things crash, why things break, and honestly, how to keep yourself alive when the universe decides to test you.
The mission statement in the intro actually gave me chills. It says, and I'm quoting here, "Physics is not optional. It is the law. You cannot negotiate with it."
That sets a tone, doesn't it?
It's a pretty intense tone for what we're about to cover.
It does, and it's accurate. We tend to move through the world with a lot of intuition. We think we know how a car stops or how water flows or what happens if we fall.
It feels natural.
But our intuition is evolved for the savannah.
Yeah.
It's based on running at maybe, 15 miles per hour? When you push the limits, highway speeds, massive forces, extreme temperatures, intuition doesn't just fail.
It gets you killed.
It gets you killed. That's the hard truth of it.
And that's the core theme for us today. It's this gap between what we feel is true and what the math knows is true. We're going to look at everything from the invisible forces that govern your GPS to the split-second decisions pilots make to avoid disaster to why you should never, ever swim if you fall into freezing water.
We're starting with how things move. That's kinematics. Then we'll get into dynamics, which is really about why they crash.
And then the really scary stuff, the invisible killers. Thermodynamics, material science, electricity.
The things you don't see coming.
So let's start at the foundation. The source calls this first big concept the trap of intuition. And it opens with something that sounds like a philosophy lecture. It's frames of reference.
It does sound philosophical, doesn't it? The idea that there is no such thing as absolute rest.
Right. I feel like I'm at rest. I'm sitting in a chair.
You might be sitting in a chair listening to this, feeling perfectly still. But relative to the sun, you're orbiting at 107,000 kilometers per hour.
Which is already a number I can't really comprehend.
And it gets worse. Relative to the center of the galaxy, our entire solar system is moving at over 800,000 kilometers per hour.
Okay, my brain just broke. But practically speaking, if I'm driving to the grocery store, I don't really care about my speed relative to the galaxy.
No.
I care about my speed relative to the cop car behind me.
For driving, sure. But here is where it gets really interesting and really critical. If engineers ignored the fact that frames of reference can differ, specifically when it comes to Einstein's theories of relativity, modern civilization would basically stop working.
That sounds like an exaggeration.
It's not, and we have a perfect example right in the research. GPS.
Okay, I rely on GPS for everything. If it goes down, I'm literally lost. But I always assumed it was just a fancy radio signal, like a triangulation thing.
It is triangulation, but it relies on timing. Impeccable timing. To know where you are, the satellite has to measure precisely how long its signal took to reach your phone.
And light travels pretty fast.
Incredibly fast.
Mm-hmm.
So that timing has to be atomic clock precise, nanosecond precise. And this is where Einstein kicks down the door.
Because the satellite is moving?
Because of how it's moving and also where it's moving. We have two conflicting laws of relativity fighting each other up there.
A tug of war.
A cosmic tug of war. First, you have special relativity. The satellite is whipping around the Earth at roughly 14,000 kilometers per hour.
And the rule is, the faster you move, the slower time passes for you. Right?
Exactly. It's called time dilation. To the satellite, its own clock is ticking perfectly normally. But from our perspective down here on Earth, that clock is ticking slower by about 7 microseconds a day. It's lagging behind us.
7 microseconds? That seems so small.
It is. But hold that thought, because now you have to deal with the other side of the equation, general relativity.
Which is about gravity.
It's about gravity. The satellite is 20,000 kilometers up. It's far, far away from Earth's heavy mass. The gravity's much weaker up there. And Einstein proved that gravity literally drags on time. Less gravity means time speeds up.
So the speed is slowing the clock down, but the lack of gravity is speeding it up.
Exactly, the constant battle. And in this case, the gravity effect is stronger.
So it wins the tug of war.
It wins. It speeds the clock up by about 45 microseconds a day. So now you do the math. You've got plus 45 from gravity's effect and minus 7 from the speed effect.
Okay, so that gives you a net error of plus 38.
A net error of 38 microseconds. The satellite's clock runs fast by 38 microseconds every single day.
38 microseconds? I mean, I honestly can't even blink in 38 microseconds. It still sounds like a rounding error. Why does the source treat this like a complete catastrophe?
Because light is fast,
Mm.
mind-bendingly, incredibly fast. And your GPS works by timing how long it takes that light speed signal to reach you.
Okay.
In 38 microseconds, light travels about 11.4 kilometers.
Whoa. Wait, say that again? 11 kilometers?
Yes, 11.4 kilometers.
Yeah.
So if the engineers didn't program a physics patch to intentionally slow those satellite clocks down before they ever launched them,
The error would build up.
it would build up by 11.4 kilometers per day.
So after one day, I turn on Google Maps and it thinks I'm in the middle of a lake in the next county over.
Worse, the next day, you're 22 kilometers off. The day after that, 33. The entire system becomes completely useless in a matter of hours.
Every Uber, every ambulance.
Every guided missile, every ship navigating the ocean, the entire global economy, which relies on synchronized timing and location, would grind to a halt. All because of a 38 microsecond drift that our intuition tells us should be meaningless.
That is a perfect example of what we're talking about. We think relativity is this abstract sci-fi thing for black holes, but it's literally the difference between me finding the coffee shop and me driving into a swamp.
Precisely. It's the difference between function and catastrophic failure. And this theme of calculating reality over trusting what you see leads us to another really intense concept in kinematics, the difference between velocity and displacement.
And this brings us to aviation. I found this part of the source material just fascinating. It's something called the $1 decision.
Oh, yes.
This is described as a point of no return. I've heard pilots talk about this, but I never, ever understood the physics behind it.
This is probably one of the most high-pressure, high-stakes decisions a human being can possibly make.
Set the scene for me.
Okay. Imagine you're the captain of a Boeing 747. You're fully loaded, hundreds of passengers, tons of fuel. You push the throttles forward. The plane is roaring, it's shaking. You're being pushed back in your seat, accelerating down this finite strip of asphalt.
Okay, I'm in the seat.
You have two critical variables in play. First is the length of the runway. That's your displacement constraint. You have a limited distance to work with.
Right. It's not infinite.
Second is the speed you need to achieve to actually fly. That's your velocity requirement. You have to get fast enough for the wings to generate lift. V-1 is the decision speed. It's a number that is calculated with extreme precision before you even release the brakes. It depends on the plane's weight, the air temperature, the runway length, everything.
And what does that number signify? What is the decision?
It marks the absolute boundary of physics. Here is the scenario from the research. You are accelerating, an engine explodes. Fire, alarms, chaos. If that happens before you reach V-1 hub speed,
You stop.
you abort. The physics says you can. You have enough runway remaining to slam on the brakes, deploy the spoilers and reverse thrusters, and dissipate all that kinetic energy to stop safely on the pavement.
Okay, that makes sense. Engine blows, I stop the plane.
But if that engine explodes a fraction of a second after you pass V-1, the rules flip completely.
What happens then?
At that speed, you have too much momentum, too much kinetic energy. You physically do not have enough runway left to stop. It's not a question of skill. It's not about having good brakes. The math says it is impossible.
So if you try to abort after V-1,
You are guaranteed to crash off the end of the runway, likely at over 150 miles per hour, into whatever is there. A field, a building, a body of water. That's a guaranteed catastrophe.
So the pilot is in this situation where the plane is literally shaking itself apart, alarms are screaming, maybe there's fire pouring out of the wing, but because the speedometer just ticked past that magic V-1 number, they have to take off.
They must take the broken, failing plane into the air. That is the hard choice. It forces the pilot to override every single survival instinct in their body that is screaming, "Stop! Stop the danger!" and instead trust a kinematic calculation they made 10 minutes ago when everything was calm.
You fly the problem.
You fly the problem because physics says stopping is certain death. Taking off is a chance at survival.
That is absolutely terrifying. It's trusting abstract math over the most visceral, terrifying reality you can imagine.
And that tension between gut instinct and cold, hard math shows up on the road too. It's something the source calls the dilemma zone in traffic engineering.
Ah, the yellow light problem. We've all been there. You see the light turn yellow and you have that split-second panic. Do I floor it or do I slam the brakes?
Right. And most people think it's just a judgment call. But traffic engineers actually have to model this with physics to prevent what they call a type 2 dilemma zone, which is basically a trap,
Trap.
a physics trap. Let's break down the variables because it's pretty simple. You have your distance to the intersection. We can call that $6. You have your stopping distance based on your current speed,
That would
$6.
depends on my brakes, the road condition.
Right. And then you have the distance required to completely clear the intersection before the light turns red.
Okay, so ideally, I'm in a position where I can either stop safely or clear the intersection safely. One of the two.
Ideally. But there is a potential death zone. Imagine a scenario where your required stopping distance is greater than your current distance to the line. So if you hit the brakes, you're going to slide out into the middle of the intersection.
Not good.
But at the same time, the distance you'd need to travel to clear the intersection is also greater than where you are. So you can't make it through in time either.
So if I brake, I crash. If I go, I run the red light and maybe get T-boned.
Exactly. Physics guarantees failure. You cannot stop, and you cannot make it. Now, this usually only happens if the yellow light duration is set too short for the posted speed limit, which is a design flaw.
But the source makes another point.
Yes. And here's the kicker. If you are speeding, you create your own personal dilemma zone, even at a perfectly engineered intersection.
Ah, because speeding makes my stopping distance way longer.
It artificially extends your six-stop number. So you might be in a position where if you were doing the speed limit, you could have stopped easily. But because you were going 10 and 15 over, you push yourself into a zone where the laws of physics offer you no safe option.
You've mathematically eliminated your own survival options.
That's a perfect way to put it. You've erased your margin of error.
That really reframes the whole idea of speeding. It's not just about getting a ticket. And speaking of speeding, that really brings us to the next major theme in the research, which the author calls the brutality of math.
And this is where we have to talk about the squared relationship. If there's one single thing listeners need to tattoo on their brain from this entire deep dive, it is this. Kinetic energy equals 1/2 mass times velocity squared.
Key E equals 12 milliV22.
That little squared at the end is the most misunderstood and deadliest part of everyday physics.
We hear that formula a lot, but let's really unpack what the squared part means. I feel like our brains don't actually process it. We think in straight lines. 60 is a little faster than 50, 70 is a little faster than 60. It feels linear.
And that linear thinking is what gets people killed. Our intuition is wrong. So let's make it visceral. Let's use an analogy from the source material.
Okay.
Imagine you are standing on a 3-story building. It's about 30 feet up. If you jump, you hit the ground at roughly 30 miles per hour. That's going to hurt, maybe break a leg, but you'll probably survive.
Okay. So 30 miles per hour feels like a 3-story fall. I can visualize that.
Now, let's say you're driving your car at 60 miles per hour. Double the speed. In your head, your linear thinking brain might go, okay, that's like jumping from a 6-story building. Double the speed, double the height.
Yeah, that feels intuitive.
It's dead wrong. Because of the square. If you double the speed, you don't double the energy. You quadruple it.
Oh,
4 times the energy. Driving at 60 miles per hour carries the same kinetic energy as falling from a 12-story building.
12 stories. That's not a broken leg. That's something else entirely.
That's fatal. That's unsurvivable for most people. And it gets even worse. What if you're going 90 miles per hour?
So that's triple the speed of 30.
Triple the speed, but you don't triple the height. 3 squared is 9. You are now carrying the same energy as if you had fallen from a 27-story skyscraper.
That image, that actually makes my stomach turn. 27 stories.
Yes. When you are cruising down the highway at 90, your car is containing the same destructive energy as a body falling from a skyscraper. And when you hit the brakes, your brake pads and rotors have to turn all of that skyscraper-level energy into heat and bleed it off into the air.
Which explains why stopping distances aren't linear at all.
Not even close. Doubling your speed from 30 to 60 doesn't double your braking distance, it quadruples it. Tripling it to 90 makes it 9 times longer.
And this is why skid marks are such a huge deal in forensic investigations. The source had a whole section on this.
Right. A skid mark is the receipt for your kinetic energy. It's a physical record of the work done by friction to stop your car.
Let's use the example from the research. A driver hits a pedestrian.
Okay. The driver tells the cops, I was doing the speed limit, 50 kilometers per hour, The person just ran out in front of me.
A classic defense.
But the police measure the scene, and they find 45 meters of solid, dark skid marks leading up to the point of impact.
So they can use that to do the math backward.
Exactly. They can work backward from the evidence. We know the coefficient of friction for rubber on dry asphalt is about 0.7. Using the physics of work and energy, we can calculate that to leave 45 meters of rubber on the road, the car had to be going approximately 89 kilometers per hour when the brakes were applied.
So he was doing nearly double the speed limit.
And that's the smoking gun. The physics proves the negligence. You can lie to the police, you can lie to the judge, but you can't lie to the coefficient of friction. The skid marks are a permanent record of your energy.
That leads us to another deadly scenario on the road where our eyes and our intuition deceive us. The source calls it the overtaking trap.
This is all about relative velocity.
And the research argues this is the most dangerous common maneuver in driving, passing someone on a two-lane highway.
It's terrifyingly dangerous, and it's because of what the source calls the illusion.
Why is it an illusion? What am I not seeing correctly?
You're not seeing speed correctly. Your brain evolved to track gazelles or lions running at maybe 30 or 40 kilometers per hour. We are not biologically wired to accurately judge the closing speeds of two objects approaching each other at a combined 200 kilometers per hour.
200.
Think about it. You're driving at 100 kilometers per hour. The oncoming car in the other lane is also doing 100. The closing speed, the relative velocity at which you are rushing toward each other, is the sum of those two. It's 200 kilometers per hour. That's about 125 miles per hour.
But when I look down the road, the oncoming car just looks like a small dot. It doesn't seem to be moving that fast. It just gets a little bigger.
That's the optical trap. Your brain can't process the danger until it's far too late. And here's the brutal math of the pass itself. Let's say you pull out to pass a truck. Your relative speed to the truck is actually very low. Maybe you're only going 10 or 15 kilometers faster than him.
Right, so it takes a while to get around.
It takes time. The calculation of the source says it might take 12 or 13 seconds to complete the maneuver safely, get back in your lane.
13 seconds feels like an absolute eternity when you're on the wrong side of the road with a car coming at you.
It is. And in those 13 seconds, that oncoming car, which is moving at roughly 25 to 30 meters every single second, has covered over 300 meters of ground. You, in your car, have also covered nearly 400 meters.
So you add those up.
You add them up, plus a safety margin, and the source calculates that you need a clear visibility gap of almost 700 meters. That's nearly a kilometer, or close to half a mile to pass safely.
That whole kilometer, that is a huge distance. I don't think I have ever waited for a full kilometer of clear road.
Most people don't. They see a gap that looks pretty good. And that brings us to the no fluff rule from the source, which is just terrifyingly simple.
What is it?
If the gap looks just about doable, it is not.
Wow.
Because your eyes are lying to you.
Mm-hmm.
If you initiate a pass with only, say, 400 meters of visibility, thinking you can squeeze in, the physics dictates that you will have a head-on collision. There is no room for negotiation. There is no way to break out of it. It's already over.
If it looks just about doable, it is not. I'm going to remember that.
Please do.
That image of the skyscraper fall, that really leads us right into the next nightmare scenario in the notes. We're entering the section on dynamics, which is basically about forces and impacts.
Newton's laws in action?
And we have to address a myth that I think every single person has entertained at least once in their life.
The falling elevator.
The falling elevator. You're in the box, the cable snaps, you're plummeting, and your brain, in that moment of terror, goes, I'll just wait. I'll wait for the very last second, right before it hits the bottom, and then I'll jump.
The Super Mario strategy.
Exactly. I'll jump up, I'll cancel out the fall, and I'll just step off lightly as the elevator crumples around me. Why doesn't that work?
It's a simple and very sad vector addition problem.
Okay, break it down.
Let's say the elevator's been falling for just 2 seconds. That's not very long. In that time, it's already accelerated to about 45 miles per hour. That's roughly 20 meters per second. Now, be honest, are you an NBA player? Can you dunk a basketball from a standstill?
Definitely not. Not even close.
Okay, so your maximum vertical leap is probably modest. An Olympic-level high jumper can generate maybe 1.5 meters per second of upward velocity. Let's be generous and give you that.
So the elevator is falling at 20 meters per second, and I heroically jump upwards at 1.5 meters per second.
Congratulations. You have successfully reduced your impact velocity from 20 meters per second to 18.5. You are now hitting the ground at 41 miles per hour instead of 45.
I'm still dead.
you are still very, very dead. The energy transfer is catastrophic. You simply cannot generate enough upward impulse to counteract the momentum built up by gravity's constant acceleration.
So the jump is completely useless. Is
Yeah.
there anything you can do? The source mentions a strategy that sounds, well, it sounds undignified.
It's completely undignified, but it uses the physics of pressure to your
Yeah.
advantage. And the key equation here is PA equal FFA. Pressure equals force divided by area.
Okay.
The impact force is going to be massive. That's a given. We can't change that. But we can change the area over which that force is applied to your body.
What's the wrong way to do it?
The wrong way is to stand up. If you're standing, all of that immense impact force is transmitted through two tiny points, the soles of your feet. It shatters your ankles, and the force shoots directly up your legs and spine. Game over.
So you want to increase the area.
You want to maximize the area. You lie flat on your back in the middle of the floor, spread out like a starfish. You want every single square inch of your skin touching the floor. You are turning yourself into a human pancake.
Why does that help?
It distributes that massive G-force across your whole body simultaneously. Your back, your ribs, your thighs, your shoulders. Don't get me wrong, it's going to break a lot of bones, but it prevents your spine from acting like a spear and getting driven through your skull. It minimizes the pressure on any single vital organ.
So it might not save you.
It might not, but physics says it's your only statistical chance of surviving the initial impact.
Okay, from falling elevators to panic braking in a car. We talked about braking distance, but let's talk about the mechanism of grip. The source draws a really important distinction between static friction and kinetic friction.
This is the fundamental hierarchy of grip. Static friction is the grip between two surfaces that are not sliding relative to each other.
Like the contact patch of a rolling tire on the road. For that split second it touches the asphalt, it's stationary.
Exactly, it's gripping. Kinetic friction, on the other hand, is the friction between two surfaces that are sliding, like a locked-up tire screeching down the road.
And the most important part is that static friction is stronger.
Significantly stronger. The coefficient of static friction is always higher than the coefficient of kinetic friction for the same two materials.
So, and this is the ironic part, a rolling wheel actually stops you faster than a locked sliding wheel.
Yes, absolutely. And this is the entire principle behind ABS or anti-lock braking system.
Right.
When you panic and stomp on the brake pedal in an old car without ABS, the wheels lock up. You immediately transition from the good, strong static friction to the weaker kinetic friction. You are now sliding.
And two bad things happen then.
Two very bad things. First, your stopping distance gets longer because your friction is weaker. Second, and maybe more importantly, you have lost all steering control. You can't steer a sliding brick. The car is going to go wherever its momentum takes it.
Because steering relies on that static grip to change the car's direction.
Precisely. ABS is a computer that's way smarter and faster than you. It senses when a wheel is about to lock, and it rapidly pumps the brakes for that wheel. We're talking 15 times a second.
So it keeps the wheel right on the edge.
It keeps it right at the threshold of locking, but allows it to keep rolling just enough. It maintains that superior static friction. So with ABS, you stop in a shorter distance, and crucially, you can still steer around the deer or the stopped car in front of you.
So the advice is, in a modern car, stomp and steer. Don't pump the brakes yourself. Trust the algorithm.
Trust the static friction. The computer's got it.
Now, what about when we're not going straight? What about turning? The source has a section on circular motion it calls the death curves.
This brings us to a new force, centripetal force. And the equation is WTC equals mv2r.
Okay, unpack that for us.
To make a car turn, you need a force constantly pushing it toward the center of the circle of the turn. That force is the centripetal force. And on a flat road, that force comes from only one place: friction between your tires and the asphalt.
And once again, we see that little VW2R in the equation.
The squared relationship strikes again. It's everywhere. If you double your speed on a curve, the equation says you need 4 times the friction, 4 times the centripetal force to hold that same line.
The example in the research is the highway off-ramp, a classic danger zone.
A classic scenario. You're coming off the highway at, say, 100 kilometers an hour. The ramp is a tight curve. The yellow warning sign says 40, and you think, hey, that's for trucks. I could do 80 in my sports car.
I think we've all thought that.
But look at the math. 80 is double 40. So you are asking your tires to provide 4 times the force that the engineers designed the curve for.
Now, the ramp is banked, right? Tilted. That helps.
The bank helps a little. It uses a component of the car's own weight to help push it into the turn. But there is a very real physical limit. If the force your speed requires exceeds the maximum friction your tires can provide, you don't just slide a little bit wide.
What happens?
You transition instantly from static friction to kinetic friction. You lose almost all your grip at once, and you lose the centripetal force that was making you turn.
And without that force, Newton's first law takes over. An object in motion stays in motion, in a straight line.
Which means you fly off the ramp tangentially. You go straight off the curve into the guardrail or down the embankment. Those yellow speed limits on curves aren't suggestions. They're calculated physics limits based on the radius of the curve and the expected coefficient of friction.
That's a really sobering thought. Let's talk about the car itself for a minute. The source makes a strong point about why old cars, those big, beautiful steel tanks from the 50s and 60s, are called death traps.
Right?
People always say, they don't make them like they used to. That old steel was so much safer.
People say that all the time, and physics fundamentally, violently disagrees.
Why?
It comes down to something called the work-energy theorem. It's a simple idea. Work equals force times distance. I tell the FD too.
Okay, unpack that in the context of a crash.
In a crash, you have a certain amount of kinetic energy, that skyscraper energy we talked about, that must be dissipated to bring you from, say, 60 miles an hour to 0. That total energy change is fixed.
So work is constant.
The work done on your body is constant, which means force multiplied by distance must equal that fixed amount of energy. It's a trade-off.
A trade-off, I see.
It's a direct inverse trade-off. To minimize the force on your body, and it's the force that breaks your bones and ruptures your organs, you must maximize the distance over which that force acts.
And the old rigid cars?
The old cars were built like tanks. They didn't crumple. In a head-on collision, the car stopped almost instantly. So the stopping distance, the Dayton equation, was tiny. Just a few inches the metal bent, and your body traveled before hitting the solid steel dashboard.
So because Dills was incredibly small, the force had to be massive.
Catastrophically massive. All that energy was dissipated over a tiny distance, resulting in a huge, deadly force on the passengers.
And modern cars are the opposite.
Modern cars have crumple zones. The entire front end of the car is designed to act like an accordion. It's engineered to fold up and destroy itself in a controlled way.
This adds distance.
It adds nearly a meter of stopping distance. It turns a sudden, sharp impact into a longer, more gradual deceleration.
A meter doesn't sound like that much in the grand scheme of things.
In the equation, $1 is big. Increasing $1 from a few centimeters to a full meter is a monumental change. It drastically reduces the peak force dollar that reaches the passenger cabin. The car destroys itself to buy you distance. It essentially dies so that you can live.
And that connects to the idea of impulse, too, right? With seatbelts and airbags.
Same exact concept, but with time instead of distance. Impulse is force multiplied by time. GDI equals F delta T. To reduce the force of an impact, you need to extend the time over which the impact occurs.
So hitting the steering wheel.
Hitting a hard steering wheel or dashboard is an impact that happens in maybe 1/100th of a second. 0.01 Ziller. It's an almost instantaneous stop. So delta T is tiny, which means F has to be huge.
And an airbag.
An airbag is a big, soft cushion that deflates as you hit it. It slows you down over a much longer period, maybe 0.3 of a second, or 0.3s. That sounds incredibly fast, but it's 30 times longer than hitting the dashboard.
So the peak force is roughly 30 times lower.
Exactly. And that is the difference between a shattered rib cage and walking away with a few bruises.
Incredible. Moving on to section 4 in the research, rotational mechanics. We see this with a very specific and common type of vehicle, the SUV. Why are SUVs so much more prone to rolling over?
It's all about a battle of torques. A torque is a twisting force.
Okay.
When you try to turn a tall vehicle like an SUV quickly, the friction of the tires on the road creates a torque that tries to roll the car over, lifting the inside wheels.
At the same time, gravity is trying to keep it down.
Right. Gravity pulls down on the car's center of mass, creating a restoring torque that tries to keep it flat on its wheels. It's a constant fight between the flipping torque from the turn and the stabilizing torque from gravity.
And the problem with an SUV is its high center of mass.
Exactly. The higher the center of mass, the longer the lever arm for that toppling, flipping force. It's like using a longer wrench. It's much easier to turn the bolt. In this case, it's much easier to flip the car.
The source mentions roof racks as a particular danger.
This is a really practical life-saving tip. Never, ever put heavy loads on the roof rack of an SUV.
Why not? That's what it's for.
It's for light, bulky things like kayaks or skis. If you put a heavy cargo box or spare tires up there, you're raising the vehicle's center of mass even higher. you're giving the toppling torque a massive advantage in its fight against gravity.
So you could flip the car more easily.
You can lower the critical rollover speed to a point where a normal, sharp highway curve could be enough to send you into a roll. Heavy stuff always belongs on the floor of the vehicle as low and as central as possible.
Let's look at something a bit more specialized from the research: projectile motion. Specifically, as it applies to search and rescue airdrops.
Right, this is a classic Hollywood versus reality moment.
In the movies, you see the rescue plane fly right over the stranded hikers on the mountaintop, and then they push the package of supplies out the door.
Which seems intuitive. You're right above them, so you drop it. But it's completely wrong, and
Okay.
it dooms the hikers. The package, when it leaves the plane, retains the full horizontal velocity of the aircraft.
So it doesn't just fall straight down.
Not at all. If the plane is moving forward at 200 kilometers per hour, the package leaves the plane also moving forward at 200 kilometers per hour. It then follows a parabolic arc as gravity pulls it down.
So it's moving forward and down at the same time.
Exactly. The source calculates that for a plane at a typical low altitude of 200 meters, moving at 200 kilometers, that package will travel horizontally about 355 meters before it finally hits the ground.
So if you wait until you see the survivors directly below you to drop the supplies.
The supplies will land 355 meters past them, probably into a ravine or deep in the forest where they can't reach it. You have to do the calculation and drop the package way, way before you actually reach the target. You have to trust the math, not your eyes.
Speaking of things not going straight, let's talk about rivers. There's a section on crossing them, specifically in a swift water rescue scenario.
This is all about vectors. Simple vector addition, but with life or death consequences.
The scenario is you need to swim from the riverbank to someone in a fast-moving current. The instinct is just to aim for them and swim as hard as you can.
And that instinct is usually wrong. If you aim directly at a stationary victim, say someone clinging to a rock in the middle of the river, the current is constantly pushing you sideways, downstream.
So you're fighting it.
You'll end up swimming on what's called a pursuit curve, constantly having to correct your angle, swimming a much longer distance, and getting exhausted in the process.
Yeah.
You might get swept past them entirely.
So what's the correct way to do it?
You need to calculate a ferry angle. You actually aim significantly upstream of the victim. You use part of your swimming speed to counteract the current so that your resultant vector, your actual path over the ground, is a straight line directly to them.
But the source notes a crucial distinction here. It depends on whether the victim is stationary or if they're also drifting in the water.
Right. This is critical. If the victim is drifting with the water, then they are in the same moving frame of reference as you and the water. In that one specific case, aiming directly at them is the correct strategy.
Because the current is affecting you both equal.
Exactly. But if they are snagged on a rock stationary, you absolutely must aim upstream. Misjudging that one vector addition means you get swept past them, and in a rescue scenario, you might not get a second try.
We've talked about these big, massive forces, but I want to zoom in on the tiny things that are supposed to hold those forces back. The hardware. There is a section here on the physics of failure that honestly terrified me because I'm pretty sure I've made this exact mistake in my own garage.
The bolt selection mistake.
Yeah. I'm that guy who loses a bolt for the lawnmower, or worse, for a trailer hitch, and I go to the big jar of random screws in the workshop, find one that fits the hole, and think, good enough.
That is, and I don't say this lightly, essentially Russian roulette with metallurgy.
Why? I mean, steel is steel, isn't it?
Oh, not even close. This is about the critical difference between tensile strength and shear strength, and the different grades of steel designed to handle them.
Okay.
A random bolt you find in a jar, a grade 2 soft steel bolt, usually with a completely unmarked, smooth head, is made of soft, low-carbon steel. The source compares it to hard cheese.
Hard cheese. That's a comforting thought for my trailer hitch.
If you use that bolt to tow a trailer, think about the forces involved. The car is pulling forward, the trailer is pulling back. The bolt is the pin connecting them. That force isn't trying to stretch the bolt, it's trying to slice it sideways. That's shear stress.
Like a guillotine.
Exactly like a guillotine.
Right.
And a soft grade 2 bolt has almost no resistance to shear. It'll just shear off clean. It doesn't unscrew or bend first, it just decapitates. Suddenly your trailer's in the other lane of traffic.
So what's the right bolt?
You need a rated hardened bolt. A grade 8 bolt. It usually has a yellow zinc coating and 6 radial lines on the head. That's hardened alloy steel. It's been heat treated specifically to resist that slicing, shearing force.
6 lines on the head. That's the code to look for.
That's the code. If the head is smooth, it's garbage steel. Do not trust your life or anyone else's to it.
And what about tightening the bolt? The notes mention plastic deformation. I always thought tighter was better. If I'm towing something, I want that bolt cranked down as hard as I can get it.
That's the other deadly trap.
Yeah.
Metal is elastic, up to a point. When you tighten a bolt, you are stretching it like a very, very stiff rubber band. That stretch, that tension, is what creates the clamping force that holds the parts together.
But if you go too far?
If you crank on it too hard with a huge wrench, you stretch it past its yield point, or its elastic limit, it enters the plastic region.
The rubber band snaps.
Not quite. It permanently stretches. It deforms. It gets longer and thinner, like taffy. You don't feel it snap, so you think you just made it extra tight, but you have fundamentally ruined the internal crystal structure of the metal. You've taken a strong, reliable bolt and turned it into a weak, brittle noodle.
And it could fail later.
It will hold for a mile and then snap when you hit the first big bump on the highway. That's why critical components have torque specs. You tighten it to a precise tension and no more.
Let's switch from solids to fluids, floodwaters. This is a recurring nightmare in storms, people driving their cars into what looks like a shallow puddle.
The source has a simple and terrifying rule for this, the 30-centimeter rule.
What is that?
It takes only about 30 centimeters, that's just 1 foot of standing water, to make a standard car begin to float.
That seems impossible. A car weighs a ton or more.
It's Archimedes' principle. The buoyant force pushing up on an object is equal to the weight of the water it displaces. A car is basically a big hollow metal box. It has a huge surface area underneath. It doesn't need to be fully submerged to displace a ton of water. It just needs to sink a few inches.
So the water literally lifts the car up off the road.
Even if it doesn't fully float, the buoyancy lifts it just enough to dramatically reduce the normal force. That's the force of the car's weight pressing the tires down onto the road.
And we know from earlier that friction equals the coefficient μ times the normal force.
So as the normal force drops, your friction drops to almost zero. You lose your grip, you lose your steering, you lose your braking.
And then you add a current.
Now you add the current. Water is incredibly heavy. A current of just a few miles per hour exerts massive pressure. Without friction to hold you in place, the car is just a toy boat. It gets pushed sideways off the road into the deeper water.
So 30 centimeter floats a car.
And the source says 60 centimeters, just 2 feet, will wash away a heavy truck or an SUV. The rule is brutally simple. Turn around, don't drown. Never drive into floodwater. You are driving a boat that was never designed to float.
We have one more aviation scenario in the research here, and it's a grim one. The impossible turn.
This is a scenario that has killed a lot of pilots, especially student pilots. It starts with an engine failure right after takeoff.
You're low, maybe 500 or 1,000 feet up, and you're flying relatively slowly because you're in a climb. The instinct must be to turn back to the runway you just left. It's right there behind you.
It's a powerful, almost irresistible instinct. A 180-degree turn back to safety. But the physics of that turn are a death trap. To make a sharp turn, you have to bank the wings steeply.
Right.
Physics dictates that when you bank, you trade some of your vertical lift for horizontal turning force. To stay level, you have to pull back on the control stick to increase the wing's angle of attack. This increases the total load, the G-force, on the wings.
And that increased load increases the aircraft's stall speed.
Drastically. A 60-degree bank, which is very steep, increases the stall speed by 41%. So if your plane normally stalls at 50 knots, in that turn, it will now stall at 70 knots.
And since you're already flying slowly because you just took off?
That turn can raise the stall speed above your actual airspeed. The wing simply stops flying.
And at 500 feet?
One wing drops, and you enter an aerodynamic spin at 500 feet. There is zero altitude to recover. You crash vertically into the ground. It's almost always fatal.
So what is the solution? What are pilots trained to do?
Land straight ahead. It's called the controlled crash. You accept that you're not going to make it back to the airport. You use your remaining altitude and speed to pick the best possible spot in front of you, a field, a road, even a line of trees. And you fly the plane into the crash under control.
You use the crumple zones.
You use the plane's structure and the terrain to dissipate the energy, just like in a car crash. It's survivable. The impossible turn is not.
Let's head into the final section of our deep dive. The invisible killers. This is where we talk about heat, resonance, and electricity.
Thermodynamics is brutal and unforgiving. Let's start with cold water survival.
Okay, if I fall into a freezing lake, my only instinct is to start swimming as hard as I can toward the shore.
That instinct is wrong unless the shore is very, very close. The problem is that water conducts heat away from your body 25 times faster than air of the same temperature. It actively steals your body heat.
And swimming makes that process faster.
Much faster. For two reasons. First, when you swim, your body pumps warm blood from your core out to your arms and legs to power your muscles. The cold water instantly cools that blood, which then circles back to your core, dropping your body's overall temperature even faster.
So you are basically acting as your own radiator, actively cooling yourself down.
Exactly. Second, moving through the water increases the convective heat loss. You're constantly exposing your skin to new cold water molecules. The solution is the HELP position.
Heat escape lessening posture.
You pull your knees to your chest, wrap your arms around them, and just float. You minimize your body's surface area exposed to the water. You protect your core, your groin, and your armpits, which are areas of high heat loss. You just wait for rescue. It can literally double your survival time.
What about heat in a confined space? The source has a section it calls the pressure cooker bomb. This is about car radiators.
Never, ever open a hot radiator cap. Here is the physics behind that rule. The coolant inside a hot engine is under high pressure.
Right.
That pressure raises the boiling point of the water. So the liquid inside might be at 125 degrees Celsius, but it's still a liquid because of that high pressure.
It's superheated.
It's a superheated liquid. When you twist that cap, you release the pressure. It drops to normal atmospheric pressure instantly. And at 1 atmosphere, water cannot exist as a liquid at 125 degrees. It's physically impossible.
So it has to change its phase. It has to become a gas.
Instantly, the entire volume of superheated water flashes into steam, and steam occupies 1,600 times the volume of liquid water. This is a violent, explosive expansion. It's not just a leak of hot water. It's a bomb of scalding steam going off directly in your face.
Let's talk about tires again, this time with heat. Blowouts.
Specifically, the danger of underinflation. Most people think overinflating a tire is what's dangerous, but it's the opposite.
Why is a soft tire more dangerous?
An underinflated soft tire flexes more as it rolls. The sidewall bends and unbends with every single rotation.
That flexing creates friction.
Internal friction. And friction creates heat. The rubber gets hot. Inside the tire, the air gets hot. And from the ideal gas law, PV equals nRT2, as the temperature T goes up, the pressure P also goes up.
So it heats itself up from the inside.
But at the same time, that high heat is degrading the structural integrity of the rubber and the glues that hold the tread to the casing. You get this thermal runaway, and eventually the tread separates from the tire in a catastrophic blowout. Underinflation is far more dangerous.
Next up, oscillations and resonance. The source gives a terrifying example. The balcony scenario.
Every object, every structure has a natural frequency, a rhythm it likes to vibrate at. For floor beams in a building or a balcony, that frequency is often around 2 to 5 hertz,
Which also happens to be
the beat of a typical pop song.
So you have a crowd of people on a balcony all jumping or dancing in unison to the music.
If that jumping frequency matches the natural frequency of the structure, you get resonance. The amplitude of the bounce, the oscillation, doesn't just add up, it multiplies with each bounce. It can grow exponentially.
So the force on the structure becomes greater than just the static weight of the people standing on it.
Much, much greater. The dynamic load can easily exceed the structural limits of the concrete and the steel rebar. The rule is simple. If you're ever in a stadium or on a bridge or a balcony and you feel it bouncing rhythmically, not just vibrating, but bouncing up and down, leave immediately. Physics is telling you that the system is entering a destructive feedback loop.
What about sound? We've talked about squared relationships, but sound is measured on a logarithmic scale.
Decibel scale.
Yeah.
And our brains are terrible at understanding logarithms. Every 10 dB increase is a 10 times increase in the sound's intensity or power.
So 100 dB is not a little louder than 90 dB.
No, it is 10 times more intense. And 110 dB is 100 times more intense than 90 dB.
And the damage it causes is purely mechanical.
It's mechanical shearing. Inside your ear, in the cochlea, you have thousands of tiny, delicate hair cells. A loud noise is a powerful pressure wave that physically bends and shears them off. It's like mowing a lawn.
And they don't grow back.
They do not grow back. If you are around firearms or chainsaws or loud concerts without hearing protection, you are permanently destroying the physical machinery of your hearing. It's irreversible damage.
Finally, let's talk about electricity and a very strange phenomenon called step potential.
This is a weird one, and something most people have never heard of. If a high-voltage power line falls on the ground, the electricity doesn't just stop. The voltage spreads out from the wire in concentric circles.
Like ripples in a pond.
Exactly like ripples. So right next to the wire, the ground might be at 10,000 volts. A meter away, maybe it's dropped to 8,000 volts. 2 meters away, 6,000, and so on.
Okay, so there's a voltage gradient on the ground.
Right. Now, if you walk normally toward or away from the wire, your feet are separated by a distance, your stride. So one foot might land on a spot that's at 10,000 volts, while your other foot is on a spot that's at 8,000 volts.
You've created a difference between your feet.
You've created a potential difference of 2,000 volts between your own feet. And electricity always flows from a high potential to a low potential.
So the current goes up one leg.
Through your pelvis, which contains your heart and other vital organs, and down the other leg to complete the circuit. You get electrocuted just by walking.
So what is the solution? The source calls it the bunny hop.
You keep your feet together at all times. If your feet are touching each other, they are both at the same voltage point. The potential difference between them is zero. If there's no potential difference, no current can flow. So you have to shuffle with your feet touching or take tiny bunny hops to get away from the downline until you are far, far away.
It looks completely ridiculous, but it saves your life.
Physics doesn't care about dignity.
So we've covered an incredible amount of ground today, from the relativity that makes your GPS work to the thermodynamics of exploding radiators. What is the big overarching takeaway here?
It really comes down to mindset. The source material contrasts three types of people. The optimist stands under the heavy load and assumes the bolt will hold.
The pessimist stands next to him and assumes the bulb will break.
And the physicist.
What does the physicist do?
The physicist calculates the shear stress on the bolt, checks the yield strength of the steel, applies a safety factor of 3, and knows that the bolt should hold, but stands out of the line of fire anyway.
Because there are always unknown variables, a hidden crack in the metal, a manufacturing defect.
Exactly. You live like a physicist. You calculate the risks. You respect the squares and the powers and the coefficients of friction. You build in a margin of safety.
And you remember the mission statement from the beginning. Physics is the law. It cannot be negotiated with.
And that really brings us to the final thought.
Yeah.
The question for you to take away from this is, are you living your life with a calculated safety factor, or are you constantly relying on the elastic limit of your luck?
That is a question worth asking every time you get behind the wheel or step onto a balcony or see a puddle on the road. Thanks for listening to this deep dive. Stay safe out there.
Safe travels.